Okay. I am pleased to introduce Larry Widrow, who's going to be asking the question, is the Milky Way galaxy ringing? And you can explain what that means. Larry Widrow got his PhD at the University of Chicago under Michael Turner, who's a famous theoretical physicist. And I asked him what his thesis title was, and it was Superconducting Complex Strings. So he's gone quite a ways from his PhD area of research. He has also worked on magnetic fields and inflation. He was a postdoc under Bill Press at CFA, so that's where he is. He was also a postdoc at CEDA in Toronto and is now faculty at Queen's University, which is in Kingston, Ontario. It's quite a royal academy. Yes. And he's now working, as all good people in astronomy, on galactic structure and galactic dynamics. And I'm pleased to have him here. And he's brought to you today by the volunteers of Milky Way at Home, who have funded this trip to come here. So I'm thankful for that, too. So, Larry Widrow.
Thank you for the introduction, and thanks for the invitation to visit RPI. As Heidi said, I will be asking the question today, is the Milky Way ringing? And in particular, study the hypothesis that a satellite galaxy, or many satellite galaxies, or substructure in the dark matter halo has passed through the disk of the Milky Way, shown here in this image, edge-on view from our position in the Milky Way, and that this passage of a satellite has sent ripples due to the gravitational field of the satellite through the disk of the Milky Way. In fact, that we're seeing these ripples in the kinematics of stars in the solar neighborhood, and in particular in the vertical structure of the galaxy. And so I'll go through some of the kinematic evidence that we think points in this direction and some of the theoretical ideas behind this. I thought that before I did this, I'd just tell you a little bit about where I come from. So I'm at Queen's University, which is up here, just a little north and west of Watertown, New York, and a beautiful, at least at this time of year, 4.5-hour drive from Troy. So we sit again here where the Lake Ontario enters the St. Lawrence River. Our department is not much different from this one. We have about 30 faculty and 70 graduate students in the areas of astronomy and astrophysics, experimental particle astrophysics, namely the physics done at the Sudbury Neutrino Lab up in Sudbury, Ontario, and also condensed matter physics, optics, nanophysics, and engineering physics. And so I mentioned this because Heidi mentioned that there would be quite a few undergraduates and graduate students in the audience. And so if you're thinking about going on in your studies in one way or another, if you like the upstate New York area and aren't intimidated by crossing borders to a strange foreign country, then please consider Queens. So to set the stage for this talk, here's this standard picture that we have now of a spiral galaxy such as the Milky Way or Andromeda. The sun sits in a stellar disk, a gaseous disk, a disk of stars and gas that are orbiting on nearly circular orbits around the center of the galaxy. Toward the center we have a bulge, which is a centrally concentrated distribution of stars on more random orbits. And all of this is embedded in a dark matter halo, material that we don't yet know what its composition is, but at least we know something about its structure, and I'll get into that as we go on in the talk. Just to give you an idea of where this structure comes from, there's a widely accepted paradigm for the formation of large-scale structure based on the notion that the universe that we live in, the energy density in the universe that we live in, has dark matter, ordinary matter or baryonic matter, radiation, and dark energy, and this is the pie chart today that you've probably seen in many talks. But during the formation of structure, when galaxies and clusters of galaxies formed, we had more dark matter and ordinary matter radiation, and in fact this dark energy was really inconsequential until the later epochs in the history of the universe. So the idea is that we have a roughly homogeneous distribution of baryonic and dark matter But imprinted on this homogeneous distribution is a spectrum of density perturbations and velocity perturbations. And in fact, it's those perturbations that get imprinted on the cosmic microwave background, and these famous pictures that you see from WMAP or the Planck experiment showing the density perturbations that ultimately give rise to galaxies and clusters of galaxies and so forth. And so these density perturbations grow via gravitational instability to form galaxies, galaxy clusters, and superclusters. They form dark matter halos, and it's within these dark matter halos that the disk of the Milky Way and the disk of the Andromeda Galaxy and so forth then are able to form. The way we test these, and we saw that in just the movie that I previously showed, is through high-resolution n-body simulations. And so we simulate the formation of the structure from these cosmological initial conditions. What we find is that we form these dark matter halos, but you see immediately from this picture that the dark halos have substructure. So the halos have subhalos, and the subhalos have their own subhalos, and there's a whole hierarchy of substructure in the distribution of dark matter that we believe exists in the universe within which we live. And in fact, the disk of our galaxy in this model, in this theory, lives deep inside one of these dark matter halos. So a natural question to ask, and it's really the central question of this talk, is what effect does all of this substructure have on the disk of the Milky Way? The substructure is moving through the halo of the galaxy. As it passes through the disk, what does it do to the disk? And so here's a simulation, and maybe I'll just pause it. This is a simulation of an isolated disk galaxy, a galaxy model that we set up, my collaborator and I set up to model the Andromeda Galaxy, in which we began with a perfectly axisymmetric disk, central bulge, and a dark matter halo. And in this model, instead of having a smooth halo, as a theorist might do, we took some of the dark matter particles and turned them into substructure. Subhalos similar to what we see from the ab initio dark matter simulation. And so this allowed us then to study what happens to the disk of the galaxy as the substructure passes through the disk, and you can see that all of this substructure is churning up the disk. It's launching spiral-like density waves, and in fact, it leads to the formation of a bar in the center of this stellar disk. And so we get a bar that forms in the disk, and the bar seems to get locked right into the disk of the galaxy and stays there essentially from then on. You notice carefully the bar actually slows down a little bit due to the dynamical friction with the halo. Well, here's an edge-on view of the same simulation, and I think this gets to the heart of the talk. As the substructure passes through the disk, you can see that there are wave-like perturbations that are then launched in the disk. And so you imagine the disk is undulating, it has bending modes, perhaps breathing modes, it's getting squished, it's getting bent, different waves passing through the disk of the galaxy. And so the question then is, would these perturbations induced by all of this substructure turn up in some kinematic survey of the stars and the disk of the galaxy? Can we observe the effects of the substructure passing through the disk? Okay?
Why was it translating so much?
I certain what's happening there. So total momentum in the simulation is conserved, but momentum between the dark matter and the disk, one can transfer momentum between the dark matter and the disk. And so I think that's what's happened. That there's been some transfer momentum to the dark. Okay, so that was essentially the introduction. Here's the outline of the talk. I'll begin by mentioning a time-honored problem in astrophysics called the word problem. A problem in which one tries to infer the amount of dark matter in the solar neighborhood by observing the kinematics of stars near the sun. And this is really where this project began. So this is an example of a project where we started by thinking about dark matter in the solar neighborhood, and and we ended up studying something else, vertical perturbations in the disk of the galaxy. But the Oort problem is a neat way of setting up the talk, and so I'll describe that in a minute. Then I'll go into the observational evidence for perturbations in the solar neighborhood perpendicular to the galactic midplane, these vertical perturbations, and then talk a little bit about disk-satellite interactions, vertical perturbations, and some of the theoretical ideas behind it. So this problem begins with the Oort problem really begins with I think a wonderful paper by Jan Oort, Dutch astronomer, in 1932, in which he describes how he could infer the force exerted by a stellar system in the direction perpendicular to the galactic plane. And so he had this idea that he could build a theoretical model for the vertical structure of the galaxy, and then by measuring the positions and velocities of stars near the sun, say something about the force. And in fact, he talks about how a purpose of this is a derivation of an accurate value for the total amount of mass, including dark matter, corresponding to unit luminosity surrounding the sun. And so he at least had this idea that there might be more mass than what you see in visible stars. Introduced or thought about this idea of this dark matter. In fact, there's an even earlier use of the term dark matter. In 1922, another Dutch astronomer, Kapteyn, also working on a theoretical model for the galaxy, well, that hasn't quite stood the test of time as well as Oort's. But nevertheless, Kapteyn talks about how it is incidentally suggested that when the theory is perfected, it may be possible to determine the amount of dark matter from its gravitational effect. And so this is all sort of before Zwicky and Rubin and Ford, interesting references to the idea of determining the amount of mass independent of the amount of light. And so I think these are the seeds of the ideas that will become a part of modern technology. So we then come to a paper. How you will appreciate that I've switched the picture of Zwicky to something more friendly. Sort of a few months in which Zwicky is smiling. Zwicky had this idea that you could measure the mass of the coma cluster in two different ways. You could take the total amount of light in the coma cluster, multiply by some mass-to-light ratio, and get the mass of the luminous material. Or you could use the virial theorem, so you could take the velocities, line-of-sight velocities of these galaxies in the cluster, use the virial theorem that you learn in your mechanics course, and convert that to a mass. And what he found was that the virial mass was something like 500 times bigger than the luminous mass. He thought of many different ways in which one might explain this number, but suggested as one possibility that there was this dark matter between the galaxies. So this is at least the first hint of the idea of dark matter from direct observations. The real key paper, though, comes with Rubin and Ford in about 1970, in which they measured the rotation curve of the Andromeda galaxy. They find that the rotation curve is flat, and a flat rotation curve essentially implies that there's increasing mass out well beyond the visible part of the galaxy, that the mass inside a particular radius is increasing with radius even as you go past the visible part of the galaxy. And so this, they conclude, tells us that there's sort of more mass there than what you see. But mass is not crazy. It's interesting, just a small historical note, that a number of years earlier, October 62, the month I was born and also the month of the Cuban Missile Crisis, Vera Rubin, and a whole bunch of undergraduate students from nearby Georgetown College Observatory, and Jamie Burley, had a rotation curve from observations of stars in the galaxy, and observed that the rotational velocity component here, let's see, for r greater than 8 kiloparsecs, for radii beyond our position in the galaxy, the rotation curve is approximately flat. So 8 years before their famous paper, Rubin has the flat rotation curve. The decrease in the rotation curve, the decrease in rotational velocity expected for Keplerian orbits is not found. So it's not Keplerian. There's more mass there than the visible stuff inside that radius. and it is shown that systematic observational errors will not account for the shape of the curve. So she really, here, I think, has evidence for the existence of dark matter, but it wasn't until a number of years later when the implications of this, the profound implications, were really, I think, appreciated. So I think it's interesting to think about how one gets a measurement of dark matter and all of the assumptions that go into understanding something like the dark matter distribution. We begin with kinematic observations. We begin by observing the position of an object and its velocity, or some subset of those measurements. We use the positions and some assumption about the orbits. So we're only getting positions and velocities, not orbits. But we make some assumption about the orbits to say something about the acceleration, which allows us to determine the force, which allows us to determine the potential and the density from Poisson's equation. If we then solve Poisson's equation, we get the mass distribution. If we then make some assumption about the distribution of visible matter, then we can say something about the distribution of dark matter. And so there are many steps in this, many assumptions along the way. And I think it's worthwhile appreciating that when you listen to talks about that. So let's see how this works for Rubin and Ford's work. They measure a flat rotation curve. A flat rotation curve, if you assume that the objects that are tracing this rotation curve are on circular orbits, then you know the orbits. You can use Poisson's equation immediately in essentially first-year mechanics to say that the circular speed goes like 1 over the square root of the radius. This tells us how the mass interior to a given radius goes. So a flat rotation curve implies that the mass goes like r. Therefore, the density goes like r to the minus 2. But again, we had to assume that everything was on circular orbits and that the potential of the galaxy was axisymmetric. So as I said, we, over the years, learned a lot about dark matter halos by doing n-body simulations. And one of the results from n-body simulations is that the density profile of dark matter halos follows some simple analytic fitting formula. Here's the most famous one called the Navarro-Franken-White fitting formula. The density goes like 1 over r in the inner part, 1 over r cubed in the outer part. But obviously there's a transition region in between where it goes like 1 over r squared, which is exactly what Rubin and Ford need to explain flat rotation curves. So if you plot r squared times rho, when rho goes like r to the minus 2, r squared times rho is constant. So in this figure showing the density as a function of radius, where the curve is flat, you essentially get a flat rotation curve. So there seems to be a good correspondence between what we find about dark matter halos in simulations and what we need to explain flat rotation curves. Well, there are more complications that arise, and one of the major ones is the fact that you can model a flat rotation curve by a combination of the potential from the halo and the disk. But you can have different admixtures of halo and disk and get exactly the same rotation curve. This is known as the disk halo degeneracy. In fact, you can get reasonable models for a disk and halo to fit the same rotation curve where the amount of disk changes by a factor of 2. And so this is a large uncertainty, and in fact we need then to understand something about the mass to light ratio of stars in order to help break this degeneracy. So there's an entire industry of people trying to study this degeneracy and break this degeneracy. Okay, well let me now turn to the ORT problem. So the key idea in the ORT problem is that one decouples the vertical motion, the z-dependence, and ignores variations in the potential or the orbits in the plane of the disk. And so this was ORT's idea. Essentially take a region that would correspond to the solar neighborhood, so some little box of stars in the disk of the galaxy. Imagine that you're riding along with the orbit of a star as it goes around the center of the disk. And then if we focus only on the vertical motion of the stars in this small region, then there is an approximate integral of motion, E of z, which is just the z velocity squared times 1/2 plus the potential relative to the potential of the midpoint. And so an integral of motion is a key idea in terms of developing a theoretical model for the structure of this galaxy. That's what work did, and it served us well in the 80 years since. Just to understand this approximation a little bit better, let's think about what the orbit of a star would be in the disk of a galaxy. If you had a Keplerian potential, that is, if all the mass of the galaxy were located at the center, then orbits would be on closed ellipses and in a single plane. But since the mass is distributed throughout the disk of the galaxy and in a disk and not spherically symmetric, then the orbits in the plane of the disk form this rosette pattern, so they're not closed ellipses. And if you look edge on, you would see a star bobbing up and down through the midplane of the galaxy. And so you see motion vertically, and if you're riding along with a particle on a perfect circular orbit, you see stars oscillating in the radial direction and in the azimuthal direction. And so for us, riding along around the center of the galaxy, we see stars coming in sort of all directions, radially in and out from the center of the galaxy, azimuthally, and this vertical oscillation, which is what we're interested in. So you can look at just the vertical velocity of the stars, the vertical phase space of the stars. So here's the height of a star above and below the midplane of the galaxy. Here's its vertical velocity, and the star makes almost a closed orbit in this phase space, this Z-BZ phase space. And that's telling us that there's an almost or approximate integral of motion. That is, if BZ were perfectly conserved, this would be a closed ellipse in this phase-space coordinates, and this would be a straight line going across. And so there's an approximate integral of motion. And essentially, that's the basis of the order approximation. So how do we talk about stars in a system like a galaxy? What's the physics that we have to use? Well, the physics is that disk stars are, and the term we use is collisionless, which means that the stars move under the influence of the mean gravitational field of the galaxy, but that we can ignore star-star collision. So a star, you can think of the smooth mean field of the galaxy. You don't have to worry about one star whizzing by another star and sort of shooting off in some direction. That's a two-body encounter, and it turns out to be utterly negligible for galactic dynamics. We then describe the distribution of stars as a density in six-dimensional phase space, so the phase space of position and velocity. And it obeys an innocuous-looking equation known as the collisionless Boltzmann equation, which essentially says that the phase space density is conserved along the orbit of any particle. So there's a beautiful example of what this theorem tells us that you can do, I think, in a sort of third-year dynamics course, where you take a distribution of particles that are described by some simple Hamiltonian, you solve Hamilton's equations, you find that from this simple distribution, the distribution function gets wound up into this spiral pattern. But Liouville's theorem tells us that the density of particles in phase space always remains the same in this Hamiltonian system. And that essentially is happening likewise in a galaxy. Well, as I said, that equation, that innocuous-looking equation, when you actually write it out, is horribly complicated. It becomes a partial differential equation in 6 dimensions and time. We're not going to try and solve that as a PDE problem. That would be hopeless. I think a few people have tried. Heroic efforts in some reduced number of dimensions. But really what one does is solve this by n-body methods. That is, throw down a bunch of particles, let them interact gravitationally, and you're essentially doing a Monte Carlo approximation of the distribution function as it evolves. One interesting question, though, is whether you can construct equilibrium solutions to this collisionless Boltzmann equation, whether you can find solutions where the distribution function doesn't depend on time. And there are, and the key to doing this is a theorem due to genes, which says that if you take any function of the integrals of motion, then you have an equilibrium model. So the importance of integrals of motion, for example, if you take something that looks like the Boltzmann distribution, then you get r to the minus 2 for the density law. So it looks like halos are sort of isothermal. You can, in fact, build more complicated systems. So the disk bulge halo system for something like a three-component galaxy, such as the one that you see, you need more integrals of motion, so you need the energy, angular momentum, and this vertical energy that I've talked about. But you can then build a nice disk bulge halo model for spiral galaxies such as the Milky Way or Andromeda. And that's work that I've been involved in over the years. Well, if we're interested in the vertical structure, if we're interested in the work problem, then a nice place to start is a solution for just a one-dimensional system. So if all you care about is the vertical structure, then you can think about the motions in the vertical direction and the distribution of stars vertically. And then there's a beautiful analytic solution worked out first by Lyman Spitzer in 1942. You can find it as a problem in Vinny and Tremaine's textbooks. There's a course in galactic dynamics. This is a nice problem to work through. And essentially you have the potential density and distribution function which solve the Poisson equation in this collision, this Boltzmann equation. It gives you a system that has high density in the midplane, and the density falls off, and the potential is this sort of harmonic potential here and linear potential in the outer part. So if you were doing electrostatics, this would be sort of a thick, infinite plane. If you wanted to translate it to So here's the org problem then. Instead of thinking about a single component isothermal system, which is Spitzer's solution, relax these assumptions. Assume that you have some observational evidence for the density and the distribution function and the velocities, and try to find the potential, the force, the density, and the distribution function that satisfy the Boltzmann equation and the Poisson equation. And if you can do that, then perhaps you can say something about the amount of dark matter in the solar neighborhood. So that's the basic idea of Ort's idea from 1942. So to do this, you actually need all of the phase space information about stars in the solar neighborhood. You need to know its position and its velocity. And in astronomy, that's very difficult to do. You can get the angular position of an object very easily by just seeing where the telescope points. Getting the distance requires some hard work. Getting the radial velocity isn't too bad because we usually use a Doppler type effect. Getting the proper motion is challenging, but we now have, well, beginning really with Hipparcos, which is the first to get lots and lots of proper motions, and now with a new satellite that's able to get more and more proper motions, surveys in between, we're able to get more and more proper motion. You can actually piece together the full six-dimensional phase space information. And so the solar neighborhood, nearby stars, is one place where you can actually do this and get proper motion for stars. So this takes me to the survey that we used for our study, which is the Sloan Digital Sky Survey. And Sloan was a dedicated 2.5-meter telescope designed to look for quasars and galaxies. But along the way, they were able to measure the positions and magnitudes of something close to 1 million stars in the solar neighborhood. And then there was a program called SEGWAY, the Sloan Extension for Galactic Understanding and Exploration, which provided the spectrum copper notion for a subset of SDSS stars. And from this, we have now a catalog, at least for this talk, of something like 11,000 stars in the solar neighborhood with full six-dimensional phase space. So the idea where this project began is to use Sloan to tell us something about the density distribution of stars in the solar neighborhood, the tracers of the potential. To use SEGWAY to tell us something about the velocities of those stars, at least a subset of those stars, and then to work through the Boltzmann and Poisson equations to say something about the potential and the force and ultimately the density. And then if you know something about the density of luminous matter, we can say something about the density of dark matter. And so this is the result just for the density of stars in the solar neighborhood. We find that the density does indeed rise, like the Spitzer solution at the midplane, and fall off in a shape very similar to what the Spitzer had theoretically, except that it's actually well fit by the sum of two Spitzer solutions, one for what we term the thin disk and the other for the thick disk. And so there seems to be two components to the disk of our galaxy. And there's been several decades of studies of trying to understand the difference between these components. and the origin of this dichotomy. What interested us, or in fact frustrated us quite a bit, is that if you look at the residuals of our fit to the data, you find a strong anti-symmetric about the midplane residuals. That is, there seem to be more stars in the south of the midplane, fewer stars in north of the midplane. So this funny shape, and then it reverses as you go a little bit higher above the midplane. So there seems to be a sort of wave-like perturbation as you go vertically above and below the midplane of the galaxy. The fact that it's anti-symmetric was puzzling, because if it was symmetric, well, you could just find a better fitting formula. And your fitting formula isn't good enough, but no symmetric fitting formula is going to fit this data. And anything that's anti-symmetric doesn't seem to be an equilibrium model of the galaxy, and we didn't want to consider it non-equilibrium because that would violate sort of the assumptions that went into the Oort problem. So we were stuck for a bit. But we looked at this a bit further. In fact, if you take north minus south over north plus south, kind of asymmetry function, you find this sort of wave-like pattern, sort of a short wavelength here and then a longer wavelength oscillation. And so this seemed interesting to us, that there's something going on in the distribution of stars in the galaxy. You can unwrap this a little bit, not only in the vertical direction, but radially outward. So the sun is here at 8 kiloparsecs from the center of the galaxy. You go out to about 9 kiloparsecs in our survey, and you see again this underdensity in the north, and then an overdensity in the north at different heights above the galactic midpoint. So that had us puzzled for. We also saw something curious in the velocities from the segue data. Below the midplane, there seemed to be a bulk motion away from the midplane of the galaxy. Above the midplane, there seemed to be bulk motion away from the midplane. And so the galaxy seemed to be breathing. It seemed to have this breathing mode velocity. So this puzzled us again. If the galaxy were in equilibrium, it wouldn't be doing this. In fact, Oort was clearly a very bright, forward-thinking person, understood all of this. He looked for these types of perturbations and writes on the whole the results, the absence of asymmetry. He didn't have quite the data we did back in 1932. The results are entirely satisfactory insofar as they show no systematic motions in the direction perpendicular to the galactic plane, so not what we found, but with fewer stars. The fact that the star is further than 100 parsecs from the north into the south, there appears to be no trace of systematic relative motion, lends support to the assumption stated in the first section that in the Z direction the stars are thoroughly mixed. And so this is the idea that if there's no bulk motion, then that's supporting the idea that things are in equilibrium. If you did see bulk motion, then that would violate that assumption. And that's well, other groups have found similar and in a more detailed way, similar type effects. There's a group called the Radial Velocity Experiment, a paper by Williams et al., in which they find both compression and rarefaction, depending on where in the solar neighborhood they're looking. These are bulk velocities relative to the rest frame of the galaxy. Here's the sun at 8 kiloparsecs. Here's the midplane of the galaxy. We find a kind of reversal in sign of the effect as you go from inside to outside. And the group here with Jeff Carlin and Heidi and others using Lamothe data find a rarefaction mode. So things moving toward the midplane from the south and toward the midplane from the north. And so there seems to be some interesting bulk motions in the distribution of stars. Different signs and different effects, and that's perhaps due to the fact that the different surveys are looking at different parts of the solar neighborhood. This is a complicated plot that Jeff Carlin put together, but it shows where the different surveys are looking in different projections, X and Z, Y and Z, X and Y, and so on. And I wouldn't want to try to get in detail into exactly what this plot is telling us, except to say that the different surveys are looking in different places, and it remains, I think, an open problem problem as to whether the surveys are consistent with one another and how to piece them all together to get a picture of what's going on in the solar neighborhood. I think that's a nice problem. So I think we're left with one of two possibilities to explain this. If these features are in fact real, then the density perturbations in the bulk velocity might arise from a stream of stars that's passing through the solar neighborhood. And so we see this quite a bit in the galaxy. We see things like the Sagittarius stream, which is the tidal debris from the Sagittarius dwarf galaxy, or the Orphan stream, which is some other disrupted dwarf or globular cluster or something. There's all sorts of debris in the galaxy, and perhaps the solar neighborhood has just been polluted by the stars stripped away by some dwarf galaxy. So that's one possibility. But a second possibility is that what we're seeing is actually perturbations in the disk itself. That is, something has come through and perturbed the disk, and it's the disk stars themselves that are responding to that perturbation, and that we're seeing the Milky Way ring in some way, some sort of oscillation type mode. And that's the hypothesis that I'll explore in the rest of the talk. So again, we come back to this question: what effect does all of the substructure that we believe exists in dark matter halos do to a disk that's sitting deep inside one of these halos? In addition, we know that some of this substructure harbors dwarf galaxies, and some of this substructure actually is visible in the form of dwarf galaxies like the large and small National Cloud or Sagittarius. And so what does this stuff do as it passes through the disk? Well, let's go a little bit into the physics and dynamics of collisionless matter. As I mentioned earlier, in any self-gravitating system, perturbations grow if gravity dominates over pressure. So that's the key idea. If you have density perturbations that are on a very large scale, and if those density perturbations can dominate over any sort of pressure force to prevent it from collapsing, then you form structure. And that's what we see in the early universe. In a stellar system, pressure arises from the random motion of stars. So it's not gas pressure, it's just random motion, which has the same effect as pressure. This leads to an important idea in cosmology and galactic dynamics called the Jeans length, which says that there's a scale, and for any density perturbation whose scale is smaller than the Jeans length, those perturbations will just sort of oscillate. Not going to be interesting, but scales larger than the Jeans length are going to collapse and form structure. And so one of the ideas that we realized immediately is that in the vertical structure of the galaxy, any perturbation that you try to put in is smaller than the Jeans length, and so any perturbation that you put in the vertical structure is just going to oscillate. You can't cause clumpiness in the vertical structure of the galaxy, only oscillations and perturbations. And all of the scale of the vertical structure is much less than 2 kiloparsecs. And so any sort of ripples that you put in the vertical structure is going to In the plane of the galaxy, though, you can develop all sorts of instabilities which drive perturbation. And so here's an example of it, this galaxy, in which goes unstable to all sorts of spiral structure, and then the formation of a bar, and then in fact the bar just kind of settles in, and the whole disk readjusts itself. So here's an example of it, this galaxy, which has one of these instabilities in it, similar to the Jeans instability, and forms both spiral structure and ultimately a bar in the center of the galaxy. If we make this particular disk model was unstable to the formation of the bar, but if we make the disk a bit lighter, then the disk will be stable to bar formation. So here again is this simulation that I showed at the beginning of the talk. This is actually a model for Andromeda that was stable to the formation of bar if I didn't put in any of this substructure. But it seems that even if the disk is stable against the formation of bar in a smooth halo, if I put in lots of substructure, it churns up the disk, and ultimately this substructure can trigger the formation of the bar. So substructure can have a dramatic effect on the structure of the disk, it can cause things like a bar to form and spiral density waves and so forth and so on. Substructure can really change what happens to the disk in the galaxy seconds. And so we took this simulation and we asked, well, with all this substructure passing through the disk, do we see perturbations in the velocity and the density that looks something like what we see in the data? And the first thing we realized is that these simulations, even though they were high-resolution simulations, don't have the resolution that we have in the data. We actually are observing so many stars in the solar neighborhood that we can't possibly resolve the types of effects that we see in the data with a simulation like this. But we're close, and we can start to see a little bit about this density, asymmetry, and velocity perturbation. So we can see hints of perturbations similar to the data, but perhaps more simulations are necessary. Here's an example where we think in the simulations we're actually seeing something very close to what we find in the data. Here's the Williams et al. Simulation. Here's this rarefaction mode, stuff moving toward the plane, inside the sun, away from the plane, outside the sun. And then here's a piece of one of these simulations where we see a similar effect. Stuff moving toward the plane, inside, and away from the plane, outside. So perhaps the simulations and the data aren't so far apart. So let's think a little bit about the physics of a satellite galaxy passing through the disk. Let's think a little bit about the properties of the solar neighborhood. We, as the sun, live about 8 kiloparsecs from the center of the galaxy. The typical velocity, vertical velocities of stars in the solar neighborhood is about 10 to 40 kilometers per second. The sun is orbiting around the center of the galaxy at 230 kilometers per second. And the surface density of stars in the solar neighborhood is about 5 times 10 to the 7 solar masses per kiloparsec squared. And the typical star orbits within sort of tens of parsecs to a kiloparsec from the midpoint. And so the idea is that a satellite with a comparable surface density in sync with the rotation of the Milky Way and perhaps moving through the midplane in resonance with these vertical motions of the stars will create some perturbations in the disk of the galaxy. And in fact, a group led by Purcell suggested that the Sagittarius dwarf, which is one of the famous dwarf galaxies in the Milky Way, might be the architect of spiral structure in the Milky Way. As it passes through the disk, it may have excited the bar and the spiral arms and so forth and so on in the Milky Way. So perhaps this substructure really is responsible for the detailed ways in which we look through it. You can think a little bit about what happens as a disk plunges through the midplane of the galaxy. It's going to plunge through, and as it does, the stars are going to fall in after this object. It's an effect similar to dynamical friction, which is something that famous astronomer John Sekar worked out in the 40s. And this could create a bending mode as the satellite plunges through the disk. In fact, you can do some toy model calculations for what happens when a star interacts with a satellite. So here's a calculation where we look at a star that's bobbing up and down from the midplane of the galaxy. Here's its velocity. This is a satellite passing through with a velocity greater than the maximum velocity of the stars. And the toy calculation says, take the unperturbed orbit and calculate the force from the satellite on the orbit, and then calculate the work that's done, and calculate the change in energy of the star due to the satellite. And so when you do this in this particular case, you find that there's a force on the star as the satellite passes through, and in fact there's net work done on the star. This particular star gains energy. Those of you who've taken quantum mechanics recently might recognize this as a sort of Born approximation. You can look at a star that's exactly 180 degrees out of phase in its vertical oscillations. Its force is in the opposite direction, but its velocity is also in the opposite direction. And so it also gains energy because work is force times v. And so both of these stars are going to gain energy. And that's the way one could set up a breathing mode perturbation. And so if stars on opposite sides of the distribution function in Z and dz both gain energy, then you get a breathing mode perturbation of the distribution function. So satellites that pass through quickly relative to the vertical motion of the stars should lead to a breathing mode. In fact, it's the breathing mode that we think we're seeing in the velocity perturbation. So this breathing mode perturbation of velocities may be in fact set up by a satellite passing through with the velocity that's a bit higher than the typical velocities of the stars in the disk. On the other hand, if the satellite moves through at a speed less than the velocity of the stars, then you have an opposite effect. In this case, stars 180 degrees out of phase. One star will gain energy, another star will lose energy. In fact, that leads to a bending mode perturbation. So in this case, these stars here are losing energy, these stars are gaining energy, and you get a bending mode perturbation. And so whether you get bending modes or breathing modes or some combination of the two really depends on the speed of the satellite relative to the vertical speeds of the stars. Sort of what you would expect from elementary dynamics. So this is leading us to a picture of the vertical motions in the disk of the galaxy in which we can think of different modes of perturbation. We can think of a bending mode in which we essentially just translate the whole disk in one direction or another. A breathing mode in which we squeeze the disk and then allow it to oscillate back and forth. And then you can imagine higher order modes which might give rise to the density perturbations that we think we're observing in the solar neighborhood. And so a satellite comes through and all these different modes are excited, and in fact excited in the three-dimensional disk. So here's a simulation that a graduate student of mine did in which we take a satellite galaxy and allow it to pass through an equilibrium disk. This particular simulation has such a large satellite that it basically just destroys the disk. It's not particularly useful or realistic model for the Milky Way, but nevertheless we're able to track the bending mode and breathing mode perturbations in the disk. And you can see that the satellite does indeed excite both of these modes, and then these modes are, as the satellite passes through, these modes are then sheared by the rotation of the galaxy into spiral-like patterns. And so the pattern of perturbation as a satellite passes through is something that I think deserves further study in comparison with the data. And so here's, I guess this is just the final print. Again, this is the bending mode perturbations, positive and negative, and breathing mode perturbations. So you get both of these modes in different patterns across the disk. This is the same analysis for that simulation that I've shown before of substructure passing through the disk, turning up the disk. Again, you get a pattern of bending and breathing mode perturbations. In this particular galaxy, you get a strong bar in the center, and so the bar itself leads to a pattern of breathing mode perturbations. As the bar sweeps through the disk, it's going to cause the disk to compress in a rarefaction and compression type. And so there seems, I think, to be an interesting connection between perhaps the perturbations that one is seeing and the formation of bars and spiral structure. Okay, so let me then give a summary. We can perhaps have time for questions. There seems to be observational evidence for vertical perturbations in the kinematics of solar neighborhood stars, and now seen in 3 different surveys: the Sloan Segway survey, RAVE, and LAMOS. The galactic dynamics community is now gearing up for data from a satellite called Gaia, which was launched in December 2013, and will hopefully provide astrometric data for something like 100 million stars or so, if everything works properly. I think that's a question. Simulations will allow us to model observed pattern of perturbations and potentially constrain galactic substructure and or the structure of the disk. At present time, the simulations have not quite achieved the resolution of the data, and for particularly the resolution that you need to really study all of the different perturbations that would arise in a stellar dynamical disk. But computers are getting ever bigger and faster, and we hope to achieve truly high-resolution simulations in the near future. And I think there's a whole variety of theoretical problems that remain to be done. Vertical perturbations may represent the early stages of disk heating and thickening events. As all these satellites pass through the disk, they're going to deposit energy in the disk and cause the disk to get a little bit thicker, a little bit hotter. Generation and evolution of waves will involve all sorts of interesting physics, resonant excitation of perturbations, coherent oscillations. There's Landau damping, which has a connection to plasma physics and phase mixing, differential rotation and shear, coupling of perturbations to the disk plane, a whole range of theory problems that one can then do and study. And then let me close just to mention my collaborators. And so this work really began with Susan Gardner, who was visiting Fermilab and connected with Brian Yenny and Scott Vogelson. Susan was interested in this work problem and constraining the local distribution of dark matter. That's how we got started, and then we got sidetracked into vertical perturbations, which is often the way research goes. And we were joined by a graduate student of Scott's, Shen-Yu Chen at the University of Chicago. All of the cool movies were done by my longtime collaborator, John Davinsky. Well, except one, which is done by my student, but John is one of the real masters of in-body simulations and galactic dynamics and visualization. Lots of cool stuff on this website. And lately I've been working with a number of graduate students and undergraduates at Queens, Jared Barber, Matthew Checkers, and Chang. They're all part of a paper that's now out in monthly notices, and I continue to work with a number of other undergraduate students.
Have we observed the bar forming other galaxies, or is that like a long time scale thing? Or?
We've observed bars in many galaxies, so I think the bar fraction, depending on how people count, is something like 20 or 30 or 50% of galaxies have some sort of bar. Some of them are fairly weak and questionable, so maybe all galaxies have some bars. And an interesting question that astronomers try to ask is whether the bar fraction is changing as we go to earlier and earlier galaxies, because as you go to higher redshift or longer look-back time, we see more bars or fewer bars. So there's a bars forming as the universe evolves, and I think that's still an open question. Bars can form, but then they can also sometimes destroy themselves. So the bar fraction as a function of time in the extreme universe, I think, is still a open question.
What are the periods of these oscillations?
The period, well, the typical vertical motions of stars up and down the midplane is on the order of tens of millions of years. I think that's also sort of the typical period of oscillation. So, as you might expect, if you start to study, you take that Spitzer solution and ask what do perturbations do to it. The natural frequencies are pretty close to the typical frequencies of the stars themselves in the system. So it's all on the order of tens of millions of years. And for comparison, the orbital time of us around the center of the galaxies are 50 to 100 million years. So it's comparable to our orbital orbit around the galactic. Yep.
Is it possible that these perturbations could be entirely responsible for the thick disk?
So there's been, I guess I would say I'm not an expert in sort of the question of what are the different formation scenarios for the thick disk. One is that the thick disk is all sort of kicked up stars from the thin disk. The problem that scenario faces is the thick disk really has different metallicity.
Yeah.
And so how do you explain that they're just different stars as you go further away? sort of everything formed in the thin disk, then gravity wouldn't care whether you're heating up low metallicity or high metallicity stars. But whether you sort of heat up an early disk and then reform a thin disk or something, I guess, are still viable scenarios. And then there's the question of whether you really do have two disks, or whether it's sort of a continuum distribution, and that, that's popped up as a question in literature in the last few years.
If a satellite goes through the disk, what's like the time scale for like after the oscillations for like some kind of equilibrium?
So that's the question I think we're just starting to answer. And so I won't answer the question, I'll just tell you the two effects that will cause the perturbation to dissipate. So one is phase mixing, which includes sort of the shearing from the rotation, differential rotation of the disk, and the fact that you start with some coherent perturbation and then different parts of the perturbation oscillate at different rates. And then there's an effect called Landau damping, which says that you have some coherent perturbation in all these stars, but these stars are individual particles which behave independently, and the individual stars can have energy out of the coherent oscillations. And that's a well-known old effect from plasma physics called Landau damping, and that can cause damping of these oscillations. And so the guess is that they probably live for a few, I'm going to guess a few dynamical times, maybe an orbit or two, but eventually they're going to dissipate throughout the disk. But I think that's the key question. That's what all these simulations will try to get at.
All right, well, we thank our speaker.